You know, in the entire world of math, there's one shape that's just king. Seriously, it's the key that unlocks pretty much everything, from building massive bridges to figuring out how far away the stars are. So today, we're going to dive deep into the fundamental building block of all geometry, the triangle. Let's do it. And this right here, this is the whole idea in a nutshell. If you can master the triangle, you can take pretty much any crazy, complex geometry problem and just break it down into simple, solvable pieces. It's like the secret weapon for mathematicians, engineers, you name it. Okay, so if we're going to stick with that atom idea, before we can start building molecules and, these complex structures, we've got to understand the atom itself. So let's start at the very beginning. What is a triangle, really? I mean, on the surface, it's super simple, right? 3 sides, 3 angles. Done. But the real magic, the thing that makes it so powerful, is that one unbreakable rule. The angles on the inside always add up to exactly 180 degrees. No exceptions. And that consistency, that's where all its power comes from. But wait a second, can you just grab any 3 lines and slap them together to make a triangle? Well, it turns out the answer is no. There's a really basic fundamental rule that decides if a triangle can even exist in the first place. It's called the triangle inequality. Okay, just forget the fancy math for a second. Let's go with the gut feeling here. Imagine you've got 2 sticks in your hands and a third one lying on the ground. If your 2 sticks put together end to end aren't even as long as the one on the ground, well, there's no way they're going to be able to reach each other to form a corner, right? They'll just fall flat. That's it. That's the whole idea. The formal rule you see there, A plus B is greater than C, is just the fancy math way of saying exactly that. And listen, this isn't just some abstract rule you have to memorize for a test. It's a genuinely practical tool. It's your first checkpoint. Can this triangle even exist? And, as we're going to see in a bit, it's absolutely crucial for figuring out the possible links for a missing side. Super useful. All right, so we've figured out what a triangle is and the rules for it to even exist. The next logical question is, how do we compare one triangle to another? And that brings us to 2 really important ideas: congruence and similarity. Are they exactly the same or just kind of the same? So let's tackle congruence first. The easiest way to think about it, it's a perfect clone, an identical twin. Congruent triangles are exactly the same side lengths, same angles, the whole shebang. You could literally cut one out and place it perfectly on top of the other. They're exact copies, period. Now here's the good news. Do you have to measure all 3 sides and all 3 angles to prove they're identical? Nope. Thankfully, some clever folks figured out some shortcuts. If you know, for example, that all 3 sides match up, that's side, or SSS, then everything else has to be the same. The angles are just locked in. The same thing works for side, or angle, side, angle. And for right triangles, they get their own special one, RHS. These are basically your cheat codes for proving 2 triangles are perfect copies. Okay, huge warning here. You might have noticed one combination that's missing from that list. Side, angle. Yeah, SSA. This is the classic trap everyone falls into. Knowing 2 sides and an angle that's not between them does not, I repeat, does not guarantee they're the same. It's such a common mistake, so please watch out for that one. All right, now for the other side of the coin, similarity. If congruence is about identical twins, similarity is, well, it's more like a family photo. Same basic look, but different ages and sizes. The photo analogy is perfect. You've got a small photo and a big poster print of the exact same thing. The shape is identical, but the size is totally different. The proportions are all that matter. So how do we prove 2 triangles are similar? The rules are a little different. For example, if all 3 of their angles match up, that's AAA, then bam, they are guaranteed to be similar. It doesn't matter how big or small they are. Another way is if all their sides are in the same ratio. Like if every side on the big triangle is exactly double the length of the matching side on the small one, that also works. These are your go-to tests for similarity. And this is where similarity gets its superpower. The second you prove 2 triangles are similar, you instantly know that the ratio of their sides is equal. And that, my friends, is a total game changer. It's how you can calculate the height of a skyscraper without climbing it, or the distance across a river without swimming. You can do all sorts of incredible things just by setting up a simple ratio. It's amazing. Okay, now inside this whole world of triangles, there is one absolute celebrity. A-list, a shape so special it gets its very own incredibly powerful rule. And I think you know what I'm talking about. It's the right-angled triangle and its legendary Pythagorean theorem.
Yeah, I'm pretty sure you've heard of this one, the Pythagorean theorem. And all it is this beautifully simple relationship that connects the lengths of the three sides. But it only works in right-angled triangles. That's its special domain.
And there it is in all its glory. A squared plus b squared equals c squared. So simple, so elegant, and yeah, probably the most famous equation in all of geometry. What it's really saying is that if you draw a square on each of the two shorter sides, the area of those two squares added together will perfectly equal the area of the big square you can draw on the longest side, the hypotenuse. Kind of cool, right? Let's make this real with the classic 3-4-5 triangle. So you've got a right triangle. One short side is 3, the other is 4. Okay, so we do 3 squared, which is 9, and 4 squared, which is 16. Add them together, 9 plus 16 is 25. And what's the square root of 25? It's 5. And boom, just like that, you know the longest side has to be 5. No ruler needed. And here's a little pro tip for you, something you might see in an Olympiad problem. The theorem actually works in reverse. It's called the converse, and it's super handy. If you just have some random triangle and you check the side lengths, and it turns out that a squared plus b squared does equal c squared, then you've just proved it has to be a right-angle triangle. It's an awesome way to find a 90-degree angle when you're not sure. Okay, let's recap. We've got our atomic rules, right? We have the inequality that tells us if a triangle can even exist. We've got the tests for when triangles are identical copies or just scaled versions. And we have that amazing superpower just for right triangles. So how do we put all these pieces together to solve an actual problem? Let's try one. Here's a classic question for you. I have a triangle, and I tell you two of the sides are length 4 and length 7. The question is, what are the possible lengths for that third side? Just take a second and think about it. Which one of our rules would help here? Hint, it was the very first one we talked about. Did you get it? The key, of course, is the triangle inequality. The third side has to be shorter than the other two added together, so that's 7 plus 4, which is 11. And it also has to be longer than their difference, which is 7 minus 4, or 3. So the third side can be literally any length you want, as long as it's more than 3 and less than 11. See? That rule comes in handy. And that little example, that's why this all matters. Triangles are the ultimate problem-solving tool. They let us look at some crazy, complicated shape and just slice it up into simple, easy-to-manage pieces. They are the absolute foundation of all logic in geometry. So, if you take one thing away from this, let it be this. A hard geometry problem isn't a problem, it's a puzzle. And the secret to solving almost any of these puzzles is to look for the triangles hidden inside. Break it down into atoms. Seriously, once you start seeing things this way, you'll start noticing them everywhere. Every complex building, every design, every challenge, it's all just a big collection of these simple atoms. So the only real question left is, what puzzle are you going to solve next? Welcome to The Explainer. Today, we're diving deep into competitive geometry. We're going to build a toolkit from the ground up that will seriously change how you look at circles and angles. So you've seen them, right? Those competition problems that just look like a total mess of lines and circles. Impossible. But here's the thing. It might look like magic, but it's really not. It's all about having the right strategy. The people who crush these problems, they rely on a core set of really powerful theorems and techniques. And today, we're going to build that exact toolkit for you, piece by piece, so you can start to think just like a champion. Okay, here's our game plan. We'll define the toolkit, then we'll add 3 essential tools. After that, we'll see how to use them, and finally, what common mistakes to watch out for. All right, let's get into it. So what do we even mean by an angle chaser's toolkit? Look, this isn't about memorizing rules from a textbook. We're building a mental framework that helps you spot patterns and unlock solutions that most people would totally miss. All right, let's grab our very first tool. It's the most fundamental one, chords. You know, those straight lines that connect any 2 points on a circle. They might seem simple, but they have some incredibly useful properties. This one is huge. I mean, it's used constantly in Olympiads. Angles subtended by the same chord. It's really just a fancy way of saying any angles that spring from the 2 ends of that chord and land on the edge of the circle. If they land on the same side of the chord, they have to be equal. It's a guarantee. Now, this slide is more than just a list of facts. It's about strategy. The first 3 points, those are your core properties. But check out the 2 tricks at the bottom. This is how you start to develop that problem-solving intuition. If you spot equal angles in a problem, your brain should immediately think, I wonder if that means I have equal chords. See some nice symmetry? Dropping a perpendicular from the center is almost always a brilliant move.
Okay, on to our next tool, tangents. A tangent is just a line that skims the edge of a circle, touching it at exactly 1 point. And wow, understanding its relationship with chords can give you a massive, massive advantage.
Okay, you really want to pay attention to this one. The tangent chord theorem is absolute gold in these competitions. Why? Because it creates this surprising link between an angle that's kind of outside the circle and another angle that's way on the other side. It's a connection that unlocks problems. You know, if that formal definition feels a little weird, here's a super simple way to remember it. Just picture the tangent line as, well, as pretending it's part of the circle, and it just copies the angle from the opposite side. That little mental shortcut can make it so much easier to spot in a really complex diagram. And now for a seriously high-powered tool. This is the one the pros absolutely love, because it leads to such elegant solutions. We're talking about the cyclic quadrilateral. This is where things get really, really cool.
First off, let's be super clear on what this is. It sounds complicated, but it's not. It is simply a 4-sided shape where all 4 of its corners sit perfectly on the edge of the same circle. That's it. And boom, here it is. This is the superpower of this shape. It's a total game changer because it gives you a simple, direct equation connecting angles that might look completely unrelated. As soon as you know a shape is a cyclical quad, you know this fact about its opposite corners.
180 degrees. You need to burn this number into your brain. The second you can prove a quadrilateral is cyclic, you've just unlocked this simple and incredibly powerful equation. And get this, it works both ways. That's what makes it so incredibly versatile. If you have any random 4-sided shape, and you can show that its opposite angles add up to 180 degrees, then you've just proved it's cyclic. And now you can use all the other circle rules on it. So we've got our 3 big tools: chords, tangents, and cyclic quadrilaterals. Now let's see how they actually work. Let's see how they take a hard problem and make it almost easy. It really is all about efficiency. This example shows the difference perfectly. The long cut is working it all out from the very basics. But the shortcut, that's just knowing the theorem. The angle in a semicircle is always a right angle. This is what separates beginners from pros. It saves you so much time and mental energy. For those really tough international level problems, here's your battle plan. Step 1 is always to hunt for tangents and shapes that might be cyclic quadrilaterals. Then you use your theorems, like the tangent chord theorem, to prove that those points are in fact concyclic. Once you've proved it, you can apply that magic 180-degree rule to find the missing piece of the puzzle. Okay, before you run off and start solving problems, let's talk about the common mistakes, because having a powerful toolkit is great, but you have to use it correctly. So let's cover what not to do. So the most important thing here is being precise. Always, always double check. Are those angles on the same side of the chord? Are you sure you're using the tangent chord theorem and not mixing it up with the angle from the circle center? And the biggest one of all, never, ever just assume a shape is cyclic. You have to prove it first. All right, we'll end with one last challenge for you. Your toolkit is ready. All the information you need is right there. Think back to our second tool, that powerful tangent chord theorem. What does it tell you about the angle we're looking for? Go ahead and pause and think it through. The answer is right there in your new toolkit. Happy angle chasing!